Okay, in this video I'm going to be working three problems that will be pertinent to the homework that you're doing in Homework 4 for the Chapter 14 part. And so we looked at this problem in class, but I'll go ahead and go over it again fairly quickly. It says, in the design of a spring bumper for a 35,000-pound car, it's desired to bring the car to a stop from a speed of 5 miles an hour in a distance of 6 inches of spring deformation. Specify the required stiffness K of each of the two springs behind the bumper. The springs are undeformed at the start of the impact. Okay, so we see the car, we see the 6 inches, we see the 5 miles an hour. Let me zoom out a little bit. I think it's going to be necessary. Hang on. Okay, so for this problem in the early part of Chapter 14, we haven't dealt with potential energy yet. So we have kinetic energy, we have work done by both conservative and non-conservative forces, and we have our final potential energy. And so using our work energy equation, we'll start off with potential energy of motion, which is 1/2 mv squared. And then the spring will be doing a negative work to slow the car down. And so I don't like the way I have this printed, but this actually brought the T1 over to the other side as negative. Okay, so just be aware of that. So our starting energy when brought to the other side is negative 1/2 m v1 squared, and that's the 5 miles an hour converted into feet per second. Then our spring energy, stealing energy from the system, slowing it down, is 2 springs times a 1/2 kx squared, and this minus sign right there deals with the fact that we are in fact losing energy. Knowing our velocity, this becomes a one equation, one unknown problem where we solve for the spring rate is equal to the mass over 2, velocity over the distance squared, and mass would be 3,500 divided by 2. This was the 3,500 was the weight of the car in pounds force, divided by 32.2 gives us the mass of the car. And of course, converting 5 miles an hour into feet per second and converting 6 inches into feet, so that we have a totally consistent set of units based on pounds for force and feet for distance, and we get an 11,690 pounds per foot of that's the spring rate, and our spring rate converted into inches, maybe it's more interesting, easier to understand, is 974 pounds per inch. Of course, we said in class, we looked at this and said this is probably not the best system for stopping a car, because when the car comes to a stop, we have all this spring energy right here sitting there waiting to be released and sending the car backwards at exactly the same speed and doing who knows what additional damage. Next problem, and I will zoom in. Okay, a woman is jogging up a flight of stairs, and the stairs are 9 feet tall, and she does this entire jog in 5 seconds. So we want to determine her average power output. Okay, and we want to eventually convert all units to SI as well, just to compare power in horsepower or foot-pounds per seconds into SI units. So, woman running up the stairs, we ignore sort of the internal work that is required simply to move her legs, and we look at the overall motion, and that means she's going to rise a height of 9 feet, and she's going to do that in 5 seconds, and will be raising a weight of 120 pounds, that 9 feet, in that amount of time. Zooming out just a touch. So, power, average power, is work done divided by the time it took to do that work, or it's an energy over time. And the energy that the girl puts into running up the stairs gets turned into MGH, potential energy, and a mass of 120 pounds, and mg is 120 pounds, a height of 9 feet, a time of 5 seconds. So we have as power 216 foot-pounds per second. But when we remember that 550 foot-pounds is 1 horsepower, we see that she's putting out about 0.393 horsepower, that's pretty decent for a human. That's certainly in the ballpark of some pretty good humans. There are humans that are better. If we convert all of the input data to SI, the height of 9 feet gets turned into 2.74 meters. Her weight of 120 pounds gets turned into a force of 534 newtons. And then we'll keep seconds as our unit of time. And so our power in SI units is 534 newtons, 2.74 meters, 5 seconds, and Newton meter per second would be watts, so 293 watts, or 0.393 horsepower. And the final problem we'll look at, let me again get the zoom about right. Let's first of all notice the picture, and because I'm going to bring the picture off the screen slightly to make the words bigger. And what we have is a block on a 3-4-5 slope, and that block initially is 10 feet from contacting the spring. It would appear that the block has an initial velocity of 10 feet per second, and almost certainly the problem is going to be how far does the block slide before it comes to rest and having compressed this spring. So let's take a look at the words of the problem and confirm that. The 100-pound block slides down the inclined plane, for which the coefficient of kinetic friction is mu k is equal to 0.25. If it is moving at 10 feet per second when it reaches point A, determine the maximum deformation of the spring needed to momentarily arrest the motion. Of course, arresting the motion means bringing it to a stop. So we're not finding the total travel of the block, we're finding only the deformation of the spring. We will end up finding both, of course. Let me zoom out a touch, and we'll take a look at the solution. Let's first of all take a look at free body diagram. We have the block, we have the normal force, we have gravity, we have our slope angle theta, we have friction mu times n, which is resisting the downhill motion. And so by doing a sum of forces in the y direction, we can then come up with the normal force and come up with the friction force. So sum of forces in the y direction would have the normal force acting, and notice our coordinate system. Y is up, x is down. So normal force positive minus the weight of the block, that's mg, and this would be times the cosine of the angle, is equal to 0 because we're not accelerating in the y direction. We get a normal force of 80 pounds, and so our friction force will be mu times n. Let me zoom out a touch more so we can see our energy equation, work energy equation, a little bit better. And so now we'll use the work energy form of the equation, where all work, whether it be at springs or friction or gravity, whatever, are lumped into this work term. And we will have a starting kinetic energy, 1/2 W over 32.2 times its velocity squared. So we have 1/2 mv squared for the block to start the problem. And then our final kinetic energy on the other side of the problem, when the block does come to a stop, will be a 0 kinetic energy. Now, what kinds of things do we have doing work? And then we have to decide if they're positive or negative. And so we have friction doing work, doing negative work, trying to bring the block to a stop. So 0.25 times 80 would be the friction force. And the work done by that friction force would be a force dot distance, but the force is precisely in the direction of the motion. So this will be force times distance. And the total distance through which the friction acts is the 10 feet before it hits the spring, plus the distance that the spring compresses. So here's our primary variable. D is the distance the spring compresses. Then we also have the work done by the spring, which would be equivalent to the potential energy stored in the spring at the end of the problem. A 1/2 K times the distance the spring compresses squared. Also negative in this case because it's stealing energy from the problem. Okay. And then finally we have the potential or the work done by gravity. So we have starting kinetic energy, work removed by, or energy removed by the friction, energy removed by the spring, energy added by falling through a gravity field, and so this will be mg times h, which is the total distance traveled times the sine of the slope angle. And all of that is equal to 0 on the right hand side because we have come to rest. There is no kinetic energy. We have D showing up 3 different places, and this is a quadratic equation in D. And if we solve this equation, we are going to get 2 roots. We'll take the one that makes sense. In this case, the positive root would be the one that makes sense. And so we would say that the spring has compressed a distance of 2.56 feet. And you can check that by plugging that back into the energy equation to make sure that it works. Okay, so those are the problems that might be helpful in working the Chapter 14 portion of the homework for which you will be responsible on Monday for a potential quiz problem.